Welcome back on the class of Introduction to Solid Mechanics. So, in the last class I have discussed about shear stress in the beam, and we have seen the expression of shear stress in terms of shear force, moment of inertia, width of the section and moment of area. After that, we have computed the value of shear stress at the neutral axis and the maximum shear stress expression we have seen, and the maximum shear stress is occur in a rectangular channel is 1.5 times the average shear stress, and we have seen the maximum shear stress is occur at the neutral axis. So today I am going to discuss another section, that is circular section, and in the circular section we will see the expression of normal shear stress and the maximum shear stress and shear stress at the neutral axis. Similarly, I will discuss about the triangular channel, and same things I will discuss in triangular channel also, and after that I will discuss I section and prismatic section. So after the rectangular section that we have seen in the last class, and in the rectangular section we have seen the maximum shear stress occur at the neutral axis and the maximum shear stress is 1.5 times the average shear stress. So let us take another section, that is circular section. So if I take a circular section, and let us assume this is neutral axis, and if I take a section at a distance of y from the center, and this is the radius of the section. So shear stress at a distance y from neutral axis is nothing but V upon IB into a y bar, where V is the shear force at that point or that section, and I is the moment of inertia, and B is the width. Here B is the diameter of the section. So once we compute the value of moment of area, that is a y bar, then we can compute the expression of shear stress at any point. So moment of area a y bar is nothing but, if I take this section, so integration of y to r, from here to r, y into dA. So it is y to r, y into, and small area dA can be written as this length into this. So this can be written as, this is dy and this is dA. So if this is the radius and this is y, so this distance is square root of r square minus y square, and this one is r square, square root of r square minus y square. So this is also r square minus y square, so it is 2 times square root of r square minus y square into dy. So a y bar is y running from y to r to y square root of r square minus y square dy. So just integrate this. So let us assume, let r square minus y square is equal to x square. So minus 2y into dy is equal to 2x into dx. So when y is equal to y, x is equal to r square minus y square, and when y is equal to r, x is equal to 0, because y is equal to r, so y square minus y square is 0. So just change the integration. So a y bar is equal to, it is running from square root of r square minus y square to 0, and the value of this is 1 by square root of r square minus y square 2x dx into x minus sign. Because I have taken r square minus y square is equal to x square, so y is equal to r square minus x square. So a y bar is minus 2 by 3 x cube running from square root of r square minus y square, running from itna to 0. This is not given. This is integral of square root of r square minus y square to 0 minus 2x square dx. So a y bar is minus 2 by 3 0 minus r square minus y square to the power 3 by 2. This is 1 by 2, so 3 by 2, so it is coming 2/3 of r square minus y square to the power 3 by 2. So a y bar is 2 by 3 r square minus y square to the power 3 by 2. And the moment of inertia is, for a circular section, it is pi d4 by 64, or in terms of radius, so it is pi r4 divided by 4. Put the value of moment of inertia and a y bar. So shear stress tau is equal to V upon I B into a y bar, and putting the value of V into a y bar is 2/3 of r square minus y square to the power 3 by 2 divided by pi r4 by 4, and width can be written as 2 times square root of r square minus y square. So shear stress is 2v by 4v by 3 r square minus y square divided by r square into 1 by pi r square. So it is coming 4 by 3 v by pi r square into 1 minus y square by r square. So this is the general expression of shear stress at a distance of y from the neutral axis. So v by pi r square is average shear stress tau average, we can written as shear force by area. So area is pi by pi r square. So this equation, shear stress, can be written as 4 by 3 tau average into 1 minus y square by r square. So when the shear stress will be maximum, when this value is 0, and this value is 0 at which point? So at the neutral axis the value of y is 0. So maximum shear stress is occur how much? 4 by 3 into tau average. So this is the maximum shear stress, and maximum shear stress occurs at the neutral axis, that is when y is equal to 0. If this is the section, if I draw the shear stress diagram, so when y is equal to r, shear stress is 0. When y is equal to 0, shear stress is coming maximum. So this value is maximum shear stress, and there should be a average shear stress. So we have to compute this point, at which point from the neutral axis average shear stress is equal to the normal shear stress. So this distance is we have to compute. So this distance can be computed. Normal shear stress is how much? Normal shear stress is equal to average shear stress. Normal shear stress is 4 by 3 tau average 1 minus y square by r square, and average shear stress is v by pi r square. So this value and this value is cancelled. So 4 minus 4y square by r square is equal to 3. So 4y square by r square is equal to 1. So y is equal to r by 2. So at a distance of r by 2, from the neutral axis, this average shear stress is equal to the normal shear stress. So this is the shear stress distribution. So we can write some points. Maximum shear stress occurs in a circular section. Circular section is at neutral axis, that is when y is equal to 0, and the maximum shear stress is 4 by 3 times tau average. So in the rectangular section we have seen maximum shear stress is 1.5 times the average shear stress, but in a circular section maximum shear stress is 1.33 times the average shear stress. Similarly, normal shear stress is equal to average shear stress at y is equal to r by 2 from neutral axis. So dear learner, till now we have seen that in a circular section the average shear stress or normal shear stress is, the expression of normal shear stress is, once again the nature is parabolic, and the expression is 4 by 3 tau average 1 minus y square by r square, and the maximum shear stress occurs at the neutral axis when y is equal to 0, and the expression of maximum shear stress is 1.33 times the average shear stress. After that we have seen at which point from the neutral axis the normal shear stress is exactly equal to the average shear stress. So we have seen at a distance of y is equal to r by 2, the normal shear stress is exactly equal to the average shear stress. So after that I am going to discuss another section, that is triangular section. So in triangular section same thing I will discuss, the general expression of shear stress and the maximum shear stress occur at which point, and the shear stress at the neutral axis, and the point from the neutral axis where normal shear stress is exactly equal to the average shear stress. So I have taken a triangular section having the base width is capital B and height is h, and let us assume this is the neutral axis. So we know from the base it is at a distance of h by 3, and from the This end it is 2h by 3. I have taken a section at a distance of from the neutral axis at a section having the width is z and CG is from the neutral axis is y bar. So shear stress, expression of shear stress is V upon IB into AY bar. So I am taking from this section, I am deriving this expression of shear stress. So V upon I, B is Z, so IZ into AY bar. So area we can write, area is equal to 1 by 2 into Y into Z, means YZ by 2. And Y bar can be written as, Y bar is 2/3 of H minus 2/3 of Y. So it is coming 2/3 of H minus Y. So shear stress tau is equal to V IZ into A Y bar. So V upon I into Z, and area is YZ by 2 into Y bar is 2/3 of H minus Y. So ZZ cancel. So it is coming, shear stress is V into Y by 3I H minus Y. So this is the expression of normal shear stress. So once again it is nature is parabolic because Hy minus Y square. So the nature is parabolic. So I am interested to compute the maximum shear stress and the location of maximum shear stress from the neutral axis, or so the maximum shear stress. So for maximum shear stress, d tau by dy is equal to 0. So H minus 2y is equal to 0. So y is equal to H by 2. So at a distance of H by 2, maximum shear stress will occur. So maximum shear stress occur at mid height of triangular section, that is y is equal to H by 2. So here is different case from the last two. In rectangular section, maximum shear stress occur at the neutral axis, and in the solid circular section, maximum shear stress is also occur at the neutral axis. But here maximum shear stress is not occur at the neutral axis. It occurs at a distance of H by 2 from the neutral axis. So variation of shear stress. So variation of shear stress, the shear stress is V into Y by 3I H minus Y. So at neutral axis, we want to compute the expression of shear stress at neutral axis. So at neutral axis, Y is equal to 2/3 of H. So put the value of Y is equal to 2/3 of H. So it is coming 2V H square, and putting the value of moment of inertia is BHQ by 36. So 3 into 2 into V, Y is equal to 2/3 of H, 3 into VHQ by 36. It's coming 27. So it is 72 by 27 V upon B into H. It is capital B. So tau is equal to 72 upon 27 V upon B into H. So we can write 8 by 3 V upon BH, or we can also write as 4 by 3 V upon BH by 2. I have written because this is the area. So tau neutral axis is equal to 4/3 of average shear stress. So neutral axis where average shear stress is coming, tau average is V upon area, V upon BH by 2. So this is the expression of average shear stress. Now I want to compute the maximum shear stress. So the maximum shear stress is coming at a distance of y is equal to h by 2. So V into h by 2 into 3 into B HQ by 36 into y minus h minus y. So h minus h by 2. So it is coming V3 V by B into H. So we can write 3 by 2 V upon BH by 2. So maximum shear stress is 1.5 times average shear stress. But remember in mind that 1.5 maximum shear stress is 1.5 times tau average. It is also coming in the rectangular section, but maximum shear stress in the rectangular section is occur at the neutral axis, but here the maximum shear stress is occurring at a distance of y is equal to h by 2. So if I draw the distribution of the shear stress, so this is B and this is H, this is the neutral axis. So if I draw the distribution, this is h by 2. So the maximum shear stress this is the maximum shear stress, and here tau neutral axis, that is 4 by 3 tau average, and the maximum shear stress is 3 by 2 tau average. So this is the distribution of shear stress. So key points. The first point is maximum shear stress occur at y is equal to h by 2. Maximum shear stress is equal to 1.5 times average shear stress. Shear stress at the neutral axis is 4 by 3 times tau average. And the fourth point is distance between neutral axis, and maximum shear stress is h by 6. So this distance is h by 6. Similarly, another section is diamond section or square section in which one diagonal is horizontal. A diamond section or a square section in which one diagonal is horizontal. So this is for your home assignment. You have to compute the value of, derive the maximum shear stress. I am taking just, if this distance is h, so this distance is also h, because this is a square section and this is the neutral axis. So you have to derive the expression of shear stress. I am writing the expression of shear stress is, if diagonal is B, so shear stress is V by B HQ H minus Y into twice Y plus H. So this is the expression of shear stress you have to derive. Similarly, shear stress at the neutral axis is coming V by B into H, and the maximum shear stress, tau max is coming at a distance of h by 4, and the expression of maximum shear stress is 9 by 8 times average shear stress. 9 by 8 times average shear stress, and maximum shear stress occurs at a distance of y is equal to h by 4. So if this is h, if I take this section, so at a distance of h by 4 it is coming. So if I draw the distribution, shear stress distribution for a diamond section or a square section in which one diagonal is horizontal. So this is the neutral axis, and the maximum shear stress is occur at a distance of h by 4. If this is so this is the distribution, this is maximum shear stress, this is also maximum shear stress, and this tau max is equal to 9 by 8 times tau average. This distance is h by 4 and this distance is also h by 4. This is neutral axis, and the average shear stress, tau average, is nothing but V by B into H. So this is the diamond section. We have seen the expression of neutral maximum shear stress and shear stress at the neutral axis. So the shear stress at the neutral axis is nothing but V by BH, and the maximum shear stress is 9 by 8 times tau average, and this is the distribution of the shear stress. So dear learner, today I have discussed about the three sections. First one is circular section, second one is triangular section, and the third section is diamond section or a square section in which one diagonal is horizontal. So in the circular section we have seen the expression of normal shear stress, and we have seen that maximum shear stress is occur at the neutral axis, and the maximum shear stress is 4/3 times the average shear stress. And after that, in triangular section we have seen the expression of normal shear stress, and in triangular section we have seen the maximum shear stress is 1.5 times the average shear stress, but this maximum shear stress does not occur at the neutral axis. It occurs at a distance of h/2 from the altitude. And similarly, we have seen the shear stress at the neutral axis is 4/3 times the average shear stress. Similarly, in the diamond section, we have seen the expression of shear stress, and the maximum shear stress is 9/8 times the average shear stress, and it occurs at a distance of h/4 from the neutral axis. And similarly, shear stress at the neutral axis in the diamond section or a square section with one diagonal is horizontal is at the neutral axis is nothing but the V by capital B into H. So in the coming class I will discuss the expression of shear stress and maximum shear stress in the I section, and after that I will solve some problem related to this. So for more updates you can also visit my civil engineering blogs talktorashid.blogspot.com. So take care of your health and happy learning.